Today we are going to discuss center of mass. What is center of mass and what are its features? After that, we'll try to find out the center of mass of two particle system. We'll find the position vector of center of mass of two particle system. After that, the discrete distribution of mass, if it is given, how we can find center of mass. And if we have a continuous body, then how we find the center of mass of such bodies. So all these we'll discuss in today's discussion. Center of mass. It is the point where whole mass of a body may be assumed to be concentrated, or it is the point about which whole mass of a body may be assumed to be uniformly distributed. These are the two ways in which you can define center of mass of a body. We are taking center of mass as a point where we can think as if the entire mass of a body is concentrated, or about that particular point we can assume the whole mass of a body is uniformly distributed. So in both ways we can define. Either we can think as if the whole mass is concentrated there, or about that point it is uniformly distributed. So suppose you take a uniform rod. The center of mass of that uniform rod will lie at the midpoint of the rod. That means it will be in the middle of the rod. So we can think as if the entire mass of that rod is uniformly distributed at this particular point, or you can think as if the entire mass is concentrated at that particular point. That means instead of using this extended body, if I use concentrated point mass, that means we just squeeze that one and make it a point mass. This is the point where it should be located so that we can give the dynamics of the entire body same as that of this particular point mass. Or if you have a circular disc, then for the uniform circular disc, center of mass will lie at its center. That means we can think as if the entire mass of the disc is concentrated at that particular point. Or you can think that about this point the mass is uniformly distributed in this particular disc. So this is for center of mass. Why we are taking center of mass? What is its importance? Suppose you take a body and you take the body and it is kept into motion. Say for example, we have this a circular disc. It is suppose rolling over a surface. So that means it is moving and it is also moving. That means it is rolling there and at the same time it is moving there. That means it is going like this. This will have the different position at different points. So here, if I take any particular point, suppose I take this particular point on the disk, in that case, you'll find that it will follow the different path. Because at this point it is here, suppose the disk after some time it is at this particular position, this may move to this position. After some time it may go to this position. So the different points of this disk will follow the different path there, and their positions will be different. Now, if I suppose take any particular point which can be used to represent the entire motion of the disk, then it is definitely, you will find, it is the center of mass. That means if this disk is moving along this particular path, after this rolling over the particular surface, then center of mass will follow this particular path. Now, if I put this entire disk as a concentrated point mass, then only if the concentrated point mass is put at this particular point, it will follow the exactly same path which is followed by this particular disk. If you put that one or take the other points there, it will not be represented by this. That means whatever we take path which is followed by the center of mass, that will be representing the path followed by the body. In the same way, suppose I have a disk, or suppose in the same way suppose we have a rod and we throw the rod, so like this is the body and I throw it. So if I throw, in that case its path there, suppose it is being thrown in this way, that means after some time the rod takes position like this. After some time it will take position like this. It is like this. That means this is moving and it is taking motion like this, and ultimately it is falling here. So again you can see the different points of this. Suppose I take this one, it is having different path. This one has some different path followed there, because after some time it is possible that it may take a shape like this. That means this point will come here, or after some time it may be coming here in this particular direction. So in that case it may be taking shape like this. So it will have the different path there. Only path which is shown by the center of mass is suppose this one. That means if I put this entire rod as a concentrated point mass, this is the path followed by this concentrated point mass or center of mass, which will be giving you the exactly same path which will be followed by this extended body's any specific point, that is the center of mass. So that is the center of mass there. Suppose we want to find position vector of center of mass of two particle system. So here M1 and M2, we take the mass of two particles constituting a particular system, and these 2 point masses have their position vector R1 and R2. This is suppose the position of the center of mass, and we assume that its position vector is represented by capital R. So we want to find the expression for this capital R in terms of R1, R2, M1 and M2. So for this we take suppose F1. This is total force on M1 due to external particle. So this is net force or force on M1 due to external particles. And F12, we take it as the force on M1 due to M2. So on this particular particle of mass M1, there is two forces. One is your F1, that is due to all external particles there, and F12 is the force on M1 due to M2. Capital F1, we take it as the net force on M1. So obviously this will be equals to F1 plus F12. This is F1. Suppose I call it as equation number 1. In the same way, if you consider F2 as the total force on M2 due to external particles, F21 as the force on M2 due to M1, and capital F2 as the total force on M2. So in the same way, we can write this one as F2 equals to small f2 plus f21. This is your equation number 2. So we have got the expression for total force on M1, total force on M2. Now if I assume capital F as the total force on this two particle system, then it is your F1 plus F2. So this will be equals to F1 plus F12, F2 plus F21. Now here will have this F12 and F21 getting cancelled. Now, why it will get cancelled? F12, this is equals to minus F21. So they will get cancelled. Force experienced by M1 due to M2 will be same as force experienced by M2 due to M1, and it will be in opposite direction. So by Newton's third law, both will experience equal and opposite forces due to one another. So they will cancel out in pairs. So what we'll get? This is your F1 plus F2. It means capital F we are writing as F1 plus F2. So here from this expression, what we can conclude, total force on a system is the vector sum of the force due to external particles. Because due to internal one, what we have seen, F12 plus F21, this is 0. So that means this is indicating the sum of the internal forces. So that one will be 0, and capital F will be F1 plus F2. That means total force on a system will be only due to the external particles there. That means experienced by the particles of the system due to external sources there or external particles. So what we have got? Capital F is equals to F1 plus F2. Now how this F1 can be represented? We can write this as rate of change of momentum of the first body. So it is your dp1 dt plus dp2 dt1. We can write it as your m1 v1 plus m2 v2. Or this will be d upon dt m1 dr1 dt m2 dr2 dt. Because the velocity, we can write it as the rate of change of its position vector. This can be written as your m1 d2r dt square, m2 d2r2 dt square. As m1 and m2 are constant, so since m1 and m2 are constant, and you know that differential of c with respect to a variable, say x, cu, and we want to differentiate it with respect to x, this will be c du upon dx. Also, we can take here d2 upon dt square, m1 r1 m2 r2 it as du plus dv differential. This is how much? Du plus dx dv dx. So this is what we have written, and this is for your second one. So suppose I call this as equation number 3. Now, if I take capital F as the net force on the system, so this will be written as your d mv upon dt. This v is the velocity of center of mass, and m will be the mass of the system. That means this m is your m1 plus m2. So this is your d upon dt m, and here it is your dr upon dt. Okay, and this we can also write it as your d2 upon dt square, capital M r, where capital M is m1 plus m2, and we have already said that this r, capital R, is the position vector of center of mass. So suppose I call this as equation number 4. From equation 3 and 4, so from 3 and 4, what we get? This m vector r, this is your m1 r1 plus m2 r2, and that will give capital R as m1 r1 plus m2 r2 by capital M here, and which can be written also as m2 r2 by m1 plus m2. So this is basically the expression for position vector of center of mass of two particle system, m1 r1 plus m2 r2 divided by m1 plus m2. Position vector of center of mass r is m1 r1 m2 r2 m1 plus m2. So this is the expression for position vector of center of mass of two particle system. For n particles, suppose it is not only two particles are there in the system, we have more number of particles. So n particle system, we can just extend that one. So we can write capital R as your m1 r1 plus m2 r2 and so on up to mn rn by m1 plus m2 plus m3 and so on up to mn. So this is the expression there that we can extend for n particle system. So this is the expression for position vector for n particle system. Now here, suppose we take for two particle system. So for two particle system, if m1 is equals to m2 and that is equals to m, suppose, what you will get for r? That will be equals to m r1 vector m r2 vector by m plus m. That means it is your r1 plus r2 vector divided by 2. So that is the position vector of center of mass of two particle system where the two masses are identical. So this is how you can get position vector for two particle system there. One more thing you can observe here, it is your m1 r1 vector plus m2 r2 vector. This is your r. So for a given body of two particle system, if you consider at the position of the center of mass, if you consider here, this is suppose your position of the center of mass, here you have m1, this is your m2. So from this, if suppose one is at a distance say r1, other is your r2, and at the position of center of mass we have assumed its origin to be located there. So in that case, what you will find here, m1 r1 will be equals to m2 r2, because distribution wise if you take it will have a negative sign there, and this position vector will be 0 there. So in this case what you will get, m1 r1 equals to m2 r2, and what you will get from this one, that r2 will be equals to m1 by m2 into r1. Here just look at this one. If m1 is greater than m2, in that case what will happen, this r2 will be greater than r1. Remember, if m1 is large, in that case position vector location will be small from the center of mass. For this particular mass, it means center of mass will be located closer to the body of heavier mass. Because other way also you can check, if m1 is less than m2, then r2 will be less than r1. So what we can conclude from that, center of mass will be closer to the body of larger mass. Let's now take coordinates of center of mass in Cartesian system. So far we have just taken it in the form of their position vector. Now that one, if suppose it is expressed in Cartesian system, so suppose R1 is given as x1 I cap, y1 j cap and z1 k cap, and R2 is x2 I, y2 j and z2 k. This capital R, which is the position vector of center of mass of two particle system, this is suppose your xi, yj and zk. So just let's substitute it as vector R is your m1 r1 vector plus m2 r2 vector by m1 plus m2. So this capital R, what we can write? xi, yj, zk. This is your m1, x1i, y1j, z1k plus m2, x2i, y2j, z2k, and the whole term divided by m1 plus m2. So here, if you just rearrange the terms, we have m1 x1 plus m2 x2 by m1 plus m2 I cap, m1 y1, m2 y2 by m1 plus m2. This is your j cap, m1 z1, m2 z2 by m1 plus m2 k cap. This is basically for xi, yj and zk. So now individually if you just equate, what you will get? X will be equals to m1 x1, m2 x2 by m1 plus m2. This is for x. For y, m1 y1, m2 y2, m1 plus m2. And if you take for z, m1 z1, m2 z2 by m1 plus m2. So this is how you can get the coordinates of center of mass of two particle system in Cartesian form. Of course, if it is for n particle system, then it will be just extended. So for n particle system, what we write for x? This is basically summation mi xi by summation mi, where I will vary from 1 to n. Similarly, y coordinate will be given as summation mi yi, summation I will vary from 1 to n. And for z coordinate, summation mi zi by summation mi I varies from 1 to n. So this is how you can find the coordinate for n particle system if it is given in Cartesian form. So this is the expression for position vector of two particle system. Of course, we can extend it for n particle system. Suppose this, if we differentiate with respect to time. So differentiating with respect to time. So what we will get? dr vector by dt. This is your m dr1 dt m1, and this is your m2 dr2 dt. What does this will indicate? dr on dt. This is v. This is the velocity of center of mass. So this is your m1 v1, m2 v2. Of course, here this is divided by m1 plus m2. So this is the expression for velocity of center of mass. Similarly, if I differentiate it again, then what will get? Here you will get this. If you are differentiating, you will get acceleration. So acceleration of center of mass. This will be your m1, and then it is your a1, m2, a2 by m1 plus m2. So this is the expression for acceleration of center of mass. Now suppose for any particular system, if it is given that the body has a center of mass at rest, and if the two center of mass is not changing its position there, so in that case what we will get? m1 v1 vector plus m2 v2 vector by m1 plus m2, that will be 0. It means it is your m1 v1 plus m2 v2 will be 0 there. And otherwise you can get it in terms of this expression. Similarly, you have r vector as m1 r1 plus m2 r2 by m1 plus m2. Suppose here if this r is fixed, that means we put it to be at the same position there, that means it is not changing its position. In that case, if m1 and m2 are changing its position, in that case that will be such, if it is given that the center of mass is not changing its position, you can use this one to find the position, new position there. Or if it is not changing, if m1 is changed, then by what distance second mass which should be changed so that the center of mass remains at the same position. For such type of problem, you can take help of this relation. Similarly, if it is given that the one body is moving with this velocity, it is changing its velocity to this, with what velocity the other one should move so that the center of mass should continue to move with the same velocity, you can take help of this relation. That is the second one. So this is how you can apply it to the different problems there. These are not just simple expression of the position vector. You can find many uses of that, especially in solving the numericals and other. Also, as we have done for coordinate of center of mass of discrete distribution of masses, means we have a number of masses there, then it is given as your summation mx by summation m. Y coordinate is given as summation my by summation m, and z is given as summation mz by summation m. If you have continuous body, this is for discrete distribution of masses, for discrete distribution of masses, you can use it. But for continuous body, if you have to find, then x will be given, because you'll have to find this in form of the integration there, in terms of the integration. So it will be written as your x dm integral by integral dm. Similarly, y will be given as integral y dm by integral dm. Z coordinate will be given as your z dm integral by integral dm. So this is how you can get the coordinate of center of mass of a continuous body. This is for continuous body, this is for discrete distribution of masses. Let's see how we find center of mass for a continuous body. So for that we are taking a center of mass of a thin uniform rod. We want to find the center of mass for thin uniform rod there. So let's assume that we have a thin rod, uniform rod. It is kept along, suppose, x-axis. This is your y-axis, and origin is at one end. This rod has mass m, and L is its length. So what will get? Mass per unit length. This will be equals to m by L. Let's now consider a elementary section at a distance x from one end, that is from the origin we are taking, and its length is suppose dx. Dx is the length of the elementary section which we have taken, and this elementary section is at a distance x from one end. If you have a thin rod and you are taking a thin slice of it, how it will look like? It will look like a point. So it will be like a point mass there. So for that case, if you consider mass of elementary section, this will be equals to m by L into dx. And what will be its coordinate? Coordinate of the elementary section. So coordinate of elementary section, because it is just like a point mass, so I can assume that its location along x-axis is at a distance x, and y coordinate will be 0. So its coordinate will be x0. Now let's use the formula for finding the position of the center of mass of this continuous body. So x coordinate is given as x dm integral by integral dm. So x is its distance, and dm value we have taken that it is your m by L into dx. We have to integrate it. Similarly, integral dm will be there. This integration will run over the entire length. So lower limit will be 0 and upper limit is L. Because the extreme positions of this elementary section will be at one end here, or it may be the other end. When it is at this extreme end, so x value will be 0, and here it will be x equals to L. So limit is 0 to L. And mass will vary from 0 to capital M. So this is equals to m by L. X dx integral is your x square by 2, 0 to L, and this is your m, 0 to M. So this is your m by 2L, L square minus 0 divided by m minus 0, and that is m will get cancelled, L will get cancelled, so it is L by 2. So x coordinate is L by 2. And what about the y coordinate? Y dm integral by integral dm. So this is 0 because y coordinate was 0 here. So as the y coordinate is 0, it will be 0. It is 0 dm integral by integral dm, so it is 0. So its coordinate will be of center of mass will be L by 2 and 0. Similarly, if you put it along y-axis, then it will be your 0 and L by 2. So that way you can find its position. This time let's take, we have a non-uniform rod. Suppose it is given that there is a rod whose linear density varies as alpha plus beta x, where x is the distance from one end, alpha and beta are the constant. So this is the linear density. Linear density. Now, as you can see that linear density is, that means we are taking mass per unit length there. So here, this is depending upon x. So it is not a uniform rod there. So here, suppose in the same way we try that it is kept along x-axis, and we take an elementary section there, and this is at a distance x. Elementary length has elementary section has the length dx. So for this one, if you consider, if the linear density is given and this rod is of length L, right? So suppose if you consider the mass of elementary section, how much it will be? This will be your lambda into dx, because it is the linear density, mass per unit length, it is given there. So this into dx, this is basically dm. And its coordinate of the elementary section, coordinate of elementary section. This is once again x0. Therefore, x coordinate of center of mass will be how much? This is your x dm, center of mass of rod, by integral dm. So if you just substitute here, then what you will get? It is x and it is your dm which we have to put. Dm is how much? Lambda into dx, and this will be integrated. Similarly, this dm is again lambda into dx integral. Okay. Never think of cutting this lambda dx, because here it is a function there, x into dx. That term we have to integrate. So this is now given as your x, and for lambda we can write alpha plus beta x dx. Integration will be 0 to L. This is your alpha plus beta x dx, and this is also from 0 to L. So this is alpha. Now it is your x dx. So it is your x square by 2, 0 to L. It is beta, and it is your x square dx. So it is your x cube by 3, 0 to L. Denominator term will have alpha dx integral. So it is your alpha x, 0 to L, and this is your beta x square by 2, 0 to L. So now just substitute this. You will have alpha by 2 L square minus 0 plus beta by 3 L cube minus 0. This is your alpha L minus 0 beta by 2 L square minus 0. So this is the term there, and we can of course cancel L. So it will be your alpha by 2 plus beta by 3L. We are taking out 1L outside, and here it is your alpha plus beta by 2L. So this is for x coordinate, and y coordinate will be your y dm integral by integral dm, which is 0 dm integral by integral dm. That will be 0. So this is the x coordinate, and y coordinate will be 0 for center of mass of this rod whose linear density is not same at all points. One more thing you should remember, that center of mass of uniform body will lie at its geometrical center. Like if it is a thin uniform rod, we have seen that its center of mass lies at its midpoint. Similarly, if you have a rectangular lamina, it is thin uniform rectangular lamina, then center of mass will lie at its geometrical center. That means it will lie at the point of intersection of the diagonals there. Similarly, if you have a thin uniform circular disc, center of mass will lie at its geometrical center, that is center of the disc. Similarly, if it is your spherical shell, uniform spherical shell or uniform solid sphere, so for all center of mass for the bodies will lie at their geometrical center. This can be proved to locate the position of the center of mass, and if the derivation is not there, then you can take this one for the other cases where the numericals are given there based on their different bodies there, and if it is mentioned that the bodies are having uniform mass there or it have the uniform density. So for all such cases there, you can take the center of mass located at their geometrical center.